Hello, everyone. Thanks for joining us today. I'm Hisham Sabahi, and I'm joined here by Jorge Silva, and we are both ML engineers here at Weights and Biases. For today, Jorge is going to share insights on how Weights and Biases can enhance your CI/CD pipeline with respect to your machine learning development cycle. Please make sure to ask any questions in the chat, and we will make sure to answer them at the Q&A session at the end. This is for me, and Jorge, please take it away.
Thank you. Thank you, Hisham. And thank you, everybody, for attending the webinar today. We have a packed agenda, so let's get started. Here's what we'll cover today. I will first introduce you to some of the unique challenges associated with doing continuous integration and continuous delivery in the context of machine learning. We will compare these challenges to those in traditional software development and highlight how traditional CI/CD tools aren't sufficient to address the needs of ML practitioners today. Then I will be taking a quick detour to show you how Weights and Biases can support your journey through the ML operations landscape and the many ways in which you can leverage us as a global system of record for all of your MLOps workflows. Next, I will introduce you to the end-to-end CI/CD use case inspired by some of the customers we have on the platform. This use case will be all about automating the process of monitoring production data and comparing it to our models training data in order to test for data drift and respond accordingly. Now, if you're more interested in monitoring model performance, rest assured you will be able to apply all the same principles and recipes to that use case as well. So do pay close attention. I will end this webinar by walking you again through each one of the key steps outlined in our use case, as I share with you some code snippets and recipes that you can use to get started. Finally, we'll open the floor for answering your questions, as Hisham mentioned at the beginning, before we conclude the webinar. So, what are the challenges of CI/CD in machine learning, and how do they compare with traditional software development? Well, first, we need to define what CI/CD is. Continuous integration and continuous delivery is a well-established software engineering practice that focuses on cutting down on the manual work needed to incorporate product improvements into software applications. This paradigm results in software products that respond quickly to the ever-evolving needs of their users, providing them with tangible value. In practice, CI/CD involves setting up a series of automated steps like integrating code, running tests, and packaging updates into one or more workflows that ensure software updates roll out smoothly, reliably, and with minimal manual intervention, thus reducing delivery costs and minimizing the impacts of human error. For machine learning teams, CI/CD requires some tweaks to the traditional software development CI/CD process, but the benefits are just as vital. So, for example, while we can apply many of the same principles to machine learning, in order to fully realize the cost savings, we have to understand and be prepared for the unique challenges of automation in the domain of machine learning. So, for example, in machine learning, data is also a source. This stands in contrast with software engineering, where code is typically the only source of truth required to build an application. In ML, training output is non-deterministic, which means that when training a model multiple times, the resulting weights and biases, that's the numbers that define how the model behaves, aren't always the same, even if the code and the data haven't changed at all. So in contrast, no matter how many times a traditional software engineering application is built, if the code doesn't change, the resulting applications should be identical, meaning that there is typically no need to track the built applications. We also have a challenge in terms of scale and variability. ML models require a staggering amount of training iterations to be ready for prime time. This can be hundreds, thousands, or often far more than that. Moreover, training different models doesn't always involve completing the same number of iterations. And in contrast, building software applications typically requires a single sequence of predetermined steps. What these challenges really spell out is that we need to, on the one hand, track the progression and differences in our source datasets. And on the other hand, we also need a way to track the changes and progression of our trained models, because due to the scale of the work involved in training and the cost involved, developing a model from scratch may be prohibitively costly. So consider, for example, a model that takes 3 or 4 days to train. If you identify an issue with this model in production, will you be able to afford waiting for it to train from scratch again? Or would you rather quickly roll back to the previously deployed trained version of the model as you wait for the new model to be retrained? Now, we also need to consider the effect that scale plays in exacerbating the challenges of CI/CD in machine learning projects. So, for example, many large enterprises now have large teams of scientists and engineers focusing on each of the at least 3 main stages of the ML development lifecycle, namely data science teams that go through their own research and development cycles, focused on collecting, cleaning, balancing, aggregating, and enriching data from multiple sources in order to create golden datasets that other teams can use to train ML models. We also have, of course, the ML engineering teams who consume these golden datasets produced by data scientists and use them to experiment with different model architectures or different ways to train the model for a particular task. Finally, we also have the target of today's webinar, the ML operations engineers, who are tasked with with making sure trained models are properly integrated, evaluated, staged, and deployed as they progress through the development pipeline. So when we think of all these challenges in the context of developing machine learning models, we can quickly come to the conclusion that one of our main priorities becomes training only when absolutely necessary and only for as long as necessary. And this again stands in contrast with traditional software development, where the priority is often to build and test as soon as the code changes or on every code change. Now, all we need to define based on this priority then is what do we mean by necessary in this case? That is, for example, coming up with ways to continuously measuring the need, and to determine when, to define and determine the when, which will allow us to optimize our decisions on whether to train or not. From here, we can actually derive a number of important requirements that traditional CI/CD tools cannot typically address. And these are: how do I track my datasets? Where do I set my models? How do I know which of my trained models is in production? How do I know which datasets were used to train these models? How do I make my experiments repeatable end to end? How do I share all this knowledge in a way that my team can access it easily and reliably? And how do I facilitate the handoff of all these datasets and models to the different engineers and through my colleagues across teams? Now, before I continue, let me take a quick detour here to introduce weights and biases and how we address all of these challenges. Weights and biases is a system of record built to facilitate collaboration and reproducibility across the machine learning development lifecycle. Basically, we aim to bring order to the chaos, complexity, and scale inherent in model development, optimization, and usage. This means that you can use weights and biases to make sense of each and every one of the research and development cycles involved in your AI development work. This, of course, not only includes the training of the models, but also, as we have introduced, it includes the research and development cycles that your data scientists go through as they clean up and transform your golden data sets, as well as the CI/CD cycles that we'll be discussing today. Now, we currently do this through two main offerings. On the left-hand side here, we have the models offering, which is the foundational set of features that weights and biases was created for, and supports the traditional machine learning development lifecycle, which typically is dominated by training. On the right-hand side, we have Weave, which is a newer offering, which is optimized for workflows involving LLM usage and generative AI jobs or development. We will not be covering Weave today, but I do encourage you to take a look at the offer, and especially if you are considering the generative AI workflows in your applications. Now, those two offerings are built on a set of primitive constructs or concepts that we call weights and biases core, all of which we will look at today, including artifacts, tables, and reports. So with that out of the way, let's introduce our end-to-end use case. And let me emphasize that this is actually inspired from a real customer use case. And this involves the automatic retraining of models based on data drift. And as I said at the beginning, if you're interested in understanding how to do this for continuous performance monitoring, you can apply the same principles as well. So this is the end-to-end workflow that we'll be walking through today. Is based, as I mentioned, on a real example from one of our customers. And starting from the bottom left, we have our daily production batching job, which is collecting data from live production interactions with the model. We have that feeding candidate data sets for training to our drift detection model, which simultaneously consumes our golden dataset, our golden training dataset from the weights and biases dataset registry. So that registry is the one that in our use case, the data scientists use to publish approved datasets for training. Now, if the drift detection model detects data drift, it does a couple of things. First, it prepares a candidate training dataset and logs it to weights and biases to be versioned. It prepares a report with a programmatically created report with the details of the drift detection analysis. And then it generates an issue. In this particular case, is a GitHub issue asking or requesting review for that particular dataset from a human reviewer. Now, in our use case, our customer needed a human in the middle or human in the loop review process because they wanted to make sure that the drift in the dataset was due to actual changes in the dataset as opposed to artifacts introduced by the logging process or simply mistakes in the pipeline. Now, once the reviewer in that process or in that stage, the reviewer has the chance to approve or deny the dataset. But if they approve it, meaning they link it back to the same dataset registry on weights and biases, to then replace the previously logged dataset, we will automatically trigger a webhook or a webhook automation from weights and biases back to the CI/CD infrastructure, which will then use this newly promoted dataset to train a model and then evaluate it against the production model. And once again, if the candidate model outperforms the production model, the model itself will be automatically promoted to now the model registry. So there's two different registries involved here. Now, let's look at how this looks in practice. And before I continue, please do bear in mind that this will be a live demo. So there's a slight risk of things taking a little longer than usual, or things not quite working the way they're supposed to, but we'll get through it, no worries. So our story here begins in the weights and biases registry. So the weights and biases registry, which is the registry for my organization, includes different collections that we can use to hand off our artifacts or our assets, especially the most important assets, to the rest of the organization. So we'll start with the dataset registry. In the dataset registry, we have a couple of collections. We have the training dataset, which is the one that I've been talking about and will be involved in the cycle that I'll walk you through. But I want to spend some time to look at the source data because it will help us think through the use case specifically in terms of what the goal of the model or the final train model is. So this source data has an associated dataset card, which we can fill with information regarding the dataset itself. And in this case, we're also including information about the goal of our project, which is forecasting household power consumption based on a dataset that includes measurements from a smart meter, as well as weather measurements from the Open Weather API. Now, we can also include links to the original dataset that was used for this project. And we're also including a couple of graphs that we've logged in the process of logging this dataset to weights and biases. Now, if we click here to look at the actual experiment that logged this dataset, we can see additional details about the dataset, including some summary statistics, which show that we have a little over 500,000 samples in this dataset. The fact that the dataset includes a number of different features here, including the active power column, which is really the target for forecasting in this particular example. And then just a few different plots that help us understand how the data is distributed in our dataset, which may be helpful for data scientists to share and analyze with their colleagues. Now, we'll go back to our registry. And the next step here is, let me just close this. The next step here is to then emulate the beginning of this automated workflow. So, of course, we are not running a daily batching job in a real sense, but we have prepared a little script that allows us to trigger this workload and then look at how the different stages are executed as a result of this trigger. What I'm doing here is just executing the workflow for day number 33. I had already executed it before for day number 32, which means that I don't actually expect any drift in the data. So as soon as I trigger that workflow, I can come to my repository and then see that workflow for an emulated daily production data log has started. If I dig into that workflow, you'll see that right after dependencies are installed, we will start with batching and logging our production dataset to weights and biases. I get a convenience link here. Whoops. I get a convenience link here that directs me to how the data is being logged on weights and biases. And if I click that, what I then see is all of the different information that I'm logging as I batch this data on a daily basis. Now, the two things that I'm going to point out here is we're using tables to log these insights for the dataset. And these tables indicate that now our count for the batch has been reduced to 200. In fact, we're aggregating data that was originally collected minute by minute into a 24-hour period because we are most interested in forecasting data or active power on a day-to-day basis as opposed to minute by minute. Now, the other thing that should have happened as well is that after the batch data workflow was executed, there was also a data drift check executed right after the batch data logging finished. And then this check is already finished. There's no machine learning involved, so it's very quick. But as we expected, because we're just collecting data for the next day from the one, from the one that we simulated we had, as expected, we don't have any drift detected. However, we can still check the details of the experiment and understand how come there's no drift, which is explained very clearly with the cumulative plots for the data distribution, which show that we're basically dealing with the same data set. So there's no drift detected in any of the features we care about. Most importantly, let me just go back here. We also have created a full report, and this report will allow us to share these results. We can simply copy this link and share it with everybody else. In fact, I'll copy it now and share it in the chat, perhaps. And then if you click on that link, because the project is open, you should be able to read along with me on the this project that has been programmatically created. Now, the advantage of creating this report is that you can share it externally. So with anybody that doesn't yet have a Weights and Biases account. In fact, I'm assuming many of you may not have a Weights and Biases account. You're still able to read that report. And it facilitates then sharing insights and information with business leaders or decision makers who may want to understand where the decisions come from, but then they may not necessarily appreciate having to look through all of your experiments on weights and biases to figure out which one is the one that that is important for them to understand. Now, let's go back to the original example, and we'll batch data now for a number of days in the future, just to make sure that that we'll actually get a drift. So now I'm going to jump over 30 days in the future and then trigger that workload and then see what the result is. So let's go back here to our GitHub repo. Again, we see that the action has been started for the emulated daily production batching from and logging of data. But then this time, I'm not going to look into the insights here. I'm going to wait for the drift check job just to show you how it looks in practice. So it should be done any minute now. Yeah, it's done. And then that means that if I refresh my page, I should see the data drift check incoming. So let's take a look at that. So after dependencies are installed, which will take a few more seconds. There you go. We'll have our drift check executing. And again, we get a convenience link here to the experiment abstract on weights and biases. If I click on that link and open it, we'll see now that, temperature has likely drifted, perhaps not humidity, but definitely active power has also drifted. And if I look at my table of results, that's exactly what I see. So now the difference is that this job should have created an issue for my reviewer. So here it is. Because drift was detected, there was an additional issue created in which we are requesting review for production batch originally logged as version 41, which is now a candidate for training logged as version 11. So if we look at our issue, that's exactly what we should see. Data drift has been detected. Please review the generated drift report. And this candidate artifact version 11, which was originally logged as production data version 41, needs to be reviewed to determine if it should become the new training gold standard. So let's look at the candidate artifact. Actually, let's look first. Let's look first at the report. Again, what we can see is a summary of the results. We're testing applying a KS test with probability under 5%. And then some of our features have drifted because their p-value is under that. We, again, collect the plots programmatically. And then as a data scientist, I can decide this looks like it's an actual drift. So I'm going to go back. I'm going to go back to check the candidate on weights and biases. Again, originally logged as production version 41. But if I go to the lineage graph on weights and biases, I can see that this production artifact was eventually, after my check, logged as a new candidate for training, which is version 11. If I go to that version 11, then I can use the link to registry button to link that dataset to my registry. In this case, is a training dataset registry. Go to next step. Maybe I can tag it as candidate. No, it would be tagged as production. And then link it to the registry. Now I can view it in the registry card, where my data science team is collecting all of the reviewed and approved training data sets. And I can see the latest version. It's now tagged as prod, as I indicated. And the lineage also tells me that it comes from the version 11 of my candidate. So I can track that data set now all the way back to all of its processing up to the version 0 of the raw data that we looked at the beginning of the webinar. The other thing that I should see then is a retrain job associated to this logging. So if I go back to my GitHub Actions, maybe it's already done. No, it's still in progress. Now I have a GitHub action triggered from weights and biases to train on a promoted dataset, just because I manually promoted it, which itself involves both the training and an evaluation, which will programmatically decide whether the model outperforms the one currently in production. So there is a case in which I can promote a dataset, but the model is not promoted because it doesn't perform as expected. And that's actually what happens. So this candidate model did not perform as well as the production model, so it's not going to be linked, but I do have a link to a report on the evaluation, and perhaps it tells me the reasons why it wasn't promoted, and here it is. So I've used a table to record and compare the metrics between the production dataset and the candidate dataset, and it turns out that the metric that I care about the most, which is my R-squared, is not performing as well as I thought. So the model is not going to be promoted. The current model remains, and that's really the end of this workflow. So in our case, as we just saw, we went through the whole process, including the generation of a new issue on data drift. We had a human in the loop review cycle. The registry then triggered, the dataset registry then triggered a webhook to then kick off our a job in our training infrastructure to train a new model, evaluate it, and then this time it wasn't approved. But if it was approved, it would have been linked to the registry where all the production models or the models highlighted for staging or production are being saved. So with that, we go back to our registry where we have our production models now. And as we can see here, maybe it's evident. Let's see in the last version. Currently, locally, it's 11 a.m. So the last version was created at 9 a.m. So as we expected, no model was linked to the production registry. So let's go back to now sharing with you, walking through each one of the key steps and sharing with you how this is actually implemented with weights and biases. The first thing we need to talk about is how we initiate an experiment. And an experiment, as you saw, can be anything from training, data drift checking, data batching, evaluations. All of those things can be experiments. They don't have to be training exclusively. So that's the first thing to highlight. The way you start an experiment is first, of course, by importing the weights and biases library. Then you use the initialize or init method to articulate to the library that you want to log something from that particular workload. And then in the case of a training experiment, what we do is log the a dictionary of metrics that we care about. This is only one thing that we can, of the many things that we can do. As we saw, we can also log tables, images, and other files, including things like videos, audio files, and all of those will be rendered, and you'll be able to interact with from Weights and Biases UI. Now, we have the next step, which is batch data logging. How do we implement our daily batch logging job? And then we follow the same principle, right? We import the Weights and Biases library. We initialize the experiment. And in this case, is a batch data type experiment. So we include that in some of our configurations for the experiment. But then the key here is the log artifact method. The log artifact method is the one that allows us to save it on Weights and Biases, and also associate it with the run that created it, therefore enabling the lineage. We also have the batch, oh no, this is, the title is wrong, but this is the drift detection workload. And in this particular case, what we are doing, again, following the same pattern, importing the library, initializing our experiment, and then using the use artifact method to consume both the production batch and the golden dataset from the training dataset registry to then be able to process the drift. We then did a couple other things, including programmatically generating a report. And in this case, we use the Weights and Biases Reports API to create a function to make that report that takes some of the parameters that we collect from our experiment as we are collecting them, and uses them to create the report, which basically means defining it and then adding blocks to it. This particular example shows a markdown block, very simple markdown block, but we have blocks that enable, of course, the embedding of the data that you've logged, as well as the media that you've logged. So the key here is understanding how to use blocks to put together the reports. And then finally, I think this is the final recipe, if I am correct. Actually, no, there's one more coming. We also, on approval, we created a webhook on Weights and Biases, and this webhook triggered a task on GitHub. So the webhook, you can very quickly define it on the Weights and Biases UI, but this recipe is about how to receive that webhook and then use it to trigger a job in your CI/CD infrastructure. This particular example, of course, is for GitHub Actions. And the key here is the fact that we are both defining the workflow on GitHub Actions to allow for external triggers, which in this case has a specific name, train on promoted dataset. And also, we need to be able to parse the payload from that trigger so that we understand which artifact is the one that has been promoted. Finally, we have the linking of the model to the registry, to the models registry, once the evaluation finishes, which involves, once again, a similar pattern, importing the Weights and Biases library, initializing the experiment, now of type evaluate, and then running our comparison, calculating our metrics, of course, and then running our comparison and deciding whether we're going to link the model or not. And in the case in which the model had performed better than the production model, we would have used then the link artifact method to make sure that that model became visible to the rest of our organization as part of the approved trained models. So with that, we conclude the webinar, and I'd be happy to answer some of your questions. Hisham, do we have any questions to highlight from the chat?
There are a couple of questions about the recordings and the slides and the cookbooks. We will share them with you via email. So
I believe you may be muted, Hisham.
Can you hear me now?
Oh no, I am. Apologies. Yeah.
Yeah. So like they have a couple of questions about the recordings and the slides. We will email it to everyone on this call right after the call and when it becomes ready. The only question that we have is, do you have a smaller, simpler example, maybe that you can highlight for everyone?
It would be interesting to understand what the meaning of smaller is in this context. But maybe what may be helpful to highlight is really what I've shown here in this slide, which is the GitHub repo that is associated to this use case. This repo is open and available to everybody. Let me actually see if I can copy. I'm just going to quickly copy this and paste it on the chat. And then maybe we can highlight a little bit some of the aspects of this repo that will be important to understand as you walk through it. So, I mean, the repo is relatively easy to navigate. We have some of the workflows grouped by type. And we have the training and evaluation scripts exposed at the root. Other than that, I think I would refer you to some of our documentation and shorter clips for doing things like logging artifacts and starting experiments in order to get on board and get started with using the platform.
Absolutely. We have a follow-up question about it. The question says, can we have a test environment to test data drift example?
Yeah, so you can sign up to Weights and Biases, and it's free to sign up. I believe you get a 30-day trial, and then you can choose how to move from there. But it should be relatively plug and play. So just by cloning the repo and then defining a couple of environment variables, including your API keys, for example, for Weights and Biases, you should be able to start replaying some of these examples very quickly. We have another question. The
question says the example you showed was for a specific customer use case. Normally the process is fully automated. If so, then how is reversion handled in case something did go wrong but wasn't caught?
Yeah, that's a great question. So let's go back to the registry, which is specifically some of the things that the registry facilitates. So in the registry, we have our production models, and we have our aliases associated to those production models. The versions themselves are aliases. You will always have a latest, but this is where you can say and articulate, for example, that this is a production model. Now, the fact that I just added a production tag or a production alias to this version means that I can actually trigger an automation to package and deliver this model to production. But if the model is already in production, which will be articulated by the fact that it already has a prior alias, all I have to do if I find a problem is go back to my version 5 and then assign that alias to that version, which will consequently trigger or can trigger an automation for it to be packaged and delivered automatically. But it also removes the alias from the version 6, which means now you know which one is in production, and you can use that alias to automate the process.
Absolutely. The next question says, in the example you showed, the whole cycle was triggered by an update to the data. Suppose we can't log data artifacts for privacy reasons. What is the recommended way to trigger the CI/CD cycle?
You can then.
I think
there's a couple of things to. Yeah, go ahead. Sure.
Yeah. I think one of the ways is you still can log artifacts without logging data. So you can bring your own bucket. We can log artifacts as references. So in a way, with some biases, does not store or copy your data set into our infrastructure, but we can track it through other means. That way, you can still leverage our artifacts offering. Jorge, feel free to add into that.
Yeah, I mean, that's true. That's one way of solving it. Artifacts are saved on a separate bucket from all the metadata that is collected during experiment tracking, as Hashan mentioned. So you can bring your own bucket, and that may or may not address the privacy issue. But if that's not sufficient, then you can trigger your own webhook from wherever you are collecting your or batching your data. So as long as you let weights and biases know that something has changed, or your CI/CD infrastructure know that something has changed, the CI/CD infrastructure will be able to continue with the workload.
Awesome. I think that's all the questions that we had for today. Any last minute questions? If not, thank you all for joining. Again, keep a lookout in your inbox for the recording and the slides and the cookbooks. And happy